Hello, my name is Diego Sanchez, and I am an undergraduate student from Essex County College, working with Nathaniel Fursell of the University of Scranton and Gareth Perry of the New Jersey Institute of Technology. This presentation is on large-scale ionospheric disturbances observed using HamSCI amateur radio, SuperDARN, GNSS TEC, and Ionosondes. Traveling ionospheric disturbances are quasi-periodic variations of F-region electron density that are often associated with atmospheric gravity waves. Large-scale TIDs typically have wavelengths of over 1,000 kilometers and a periodicity of between 30 to 180 minutes, and are often caused by auroral electrojet enhancement and particle precipitation. The main data sources are the Reverse Beacon Network, which is a network of stations listening to the radio bands and reporting what stations they hear, when, and how well, and the Weak Signal Propagation Reporting Network, group of amateur radio operators using digital radio modes to probe radio frequency propagation conditions using very low power transmissions for their ham radio data. The Super Dual Auroral Radar Network, which is a network that consists of more than 30 low-power HF radars that look into Earth's upper atmosphere beginning at mid-latitudes and extending into the polar regions. The Madrigal GPS total electron content, NASA Omni data, and Ionoson FOF2 data from the Boulder and Julius Root Ionosondes. Here is a figure demonstrating what happens to an HF radio wave when it attempts to pass the ionosphere. As the ionosphere becomes perturbed, the amount of refraction changes. TIDs cause a perceived fading in HF propagation when observed using SuperDARN HF radars and ham radio data. On the top left corner, we can see a simulation of how SuperDARN radars would perceive a TID. The figure on the right shows SuperDARN beam 13 data from November 3, 2017 with a clear TID. The bottom left figure shows the location of beam 13. Since SuperDARN perceives TIDs similarly to ham radio data, we expect to see the same wave-like structures in both types of plots. This is a representation of the RBN and WhisperNet data sources. Figure A shows geomagnetic activity through the KP index. Figure B shows solar activity taken from both the GOES 13 and 15 satellites. These two figures are used to eliminate other factors such as geomagnetic storms or solar flares that could be causing disturbances in our histograms aside from a TID. Figure C and D show ham radio activity from spot data coming from both RBN and WhisperNet over a 24-hour period separated in 2-minute interval bins, with our y-axis being the skip distance of a spot and spot density represented by the color scale on the right. More yellow colors represent more spot density, while more blue colors represent less. On our left, we also have the total number of spots for this histogram, as well as the percentage of data that comes from RBN and WhisperNet. Last, we have a map of the area the spots are originating from on the bottom left corner. As you can see, we have marked with red arrows a particularly pronounced wave-like structure in our 14 MHz histogram from November 3, 2017, that we suspected could be an LSTID given the apparent periodicity and how relatively quiet that day was in terms of geomagnetic and solar activity. Since HF refraction is associated with ionospheric density, we use GPS total electron content data to see if these wave-like structures coincided with total electron content changes in the ionosphere. More red colors represent a higher total electron content, and more blue colors represent less total electron content in our GNSS TEC plots. As the minimum skip distance rises in our ham radio plots, we see a higher TEC values, and when the minimum skip distance falls, so does the total electron content. As you can see, the change in total electron content coincides with our change in minimum skip distance. Here's the comparison of the GNSS TEC from 18 hours to 21 hours UTC. We also found other days we suspected had active TIDs. This next comparison is of November 23rd, 2017 in North America. As you can see, higher minimum skip distances coincide with less total electron content, and lower minimum skip distances coincide with higher total electron content. This comparison is from January 26, 2017 in North America. Another data source we used to compare with our ham radio histograms was Ionoson FOF2 data. We tried finding ionosondes relatively close to the largest concentration of radio spots. For North America, we used Boulder, and for Europe, we used Julius Rue. On the right, we have maps of ham radio spot locations. The yellow star represents the central location relative to the total spots, and the white circle shows us the location of the ionosondes. FOF2 is the highest frequency sent from the ionosonde that reflects back from the ionosphere. The higher the frequency that is bounced back from the ionosphere, the higher the electron densities will be. This means that radio ranges will be shorter at higher FOF2 values and longer at lower FOF2 values. Here we have a comparison from January 26, 2017. As you can see, the lowest peaks in our ham radio plots coincide with the highest peaks in the ionosonde plots. This comparison is from Julius Rue in Europe on September 27, 2017. From these observations, we can conclude that the ham radio disturbances seem likely to be LSTIDs. They appear coherent across continental US and Europe. They're consistent with SuperDARN beam 13. They're also consistent with the GNSS TEC plots, as well as Boulder and Julius Rue ionosonde data. We can also conclude that RBN and WhisperNet can serve as a tool for monitoring LSTIDs during the day and night. However, there is less night observation capabilities using 14 MHz. Next in our study is to find the exact source of the detected LSTIDs. Thank you all for listening, and I hope you all enjoyed.